Good morning and welcome to the lecture number 7 of the course Water Resource Systems, Modeling Techniques and Analysis. We have been talking about optimization of multiple variables. Initially, we started with optimization of functions with no constraints. Such problems are called as unconstrained optimization problems. And then we introduced the equality constraints, that is optimization of a function of n variables with m number of equality constraints. And in the constraint optimization, where you have only equality constraints, we discussed two methods. One is the method of direct substitution, in which you will use the m equations to express m variables in terms of the remaining n minus m variables and convert the original constrained optimization problem into an unconstrained optimization problem with n minus m variables. So, essentially we eliminated the m number of variables using the m equations. And then we introduced the more rigorous Lagrange multiplier method, where corresponding to each of the equality constraint, we introduce an additional variable called the Lagrange multiplier, and then the original problem of n variables is now converted into another problem of n plus m variables with all the constraints taken into account. For the Lagrange multiplier method, we formulated the necessary conditions and the sufficiency conditions for a stationary point to correspond to either a maximum or minimum. And then we went on to state the Kuhn-Tucker conditions. So, this is what we did in the previous lecture. In the last lecture, I discussed the Lagrange multiplier method, where we formulate the Lagrange function L is equal to f of x, summation j is equal to 1 to m lambda j g j of x. The lambda j's are the Lagrange multipliers, g j of x are the constraints. So, we stated g j of x is equal to 0 as a set of m constraints, m equality constraints, and we apply the Lagrange multiplier method for equality for optimization of functions with subject to equality constraints. The necessary condition for the problem will be dl by dxi is equal to 0 with respect to all i's. That means, we take the first derivative of the Lagrange with respect to each of the variables xi, and the first derivative of the Lagrange with respect to each of the Lagrange multipliers themselves, lambda j. So, you will have n conditions here plus m conditions here. So, n plus m equations, you solve for these n plus m equations simultaneously to get x 1, x 2, x 3 etcetera x n and lambda 1, lambda 2 etcetera lambda n. Lambda m, I am sorry. So, n plus m equations, you solve for the n plus m variables. The sufficiency condition, we formulated for the sufficiency condition, we formulated the determinant d based on the second order derivatives of the Lagrange d square L by dx I dx j, evaluated at the stationary point x star lambda star, and the first order derivative of the constraint functions g j of x with respect to each of the variables x i. Using these, we formulated the determinant and equated the determinant to 0, and you get a polynomial of the order n minus m for z, which is a function in which is a variable in the determinant d. Solve for z. If all the values of z are positive, then the point x star lambda star corresponds to a minimum. If all the values of z are negative, the point x star lambda star corresponds to a maximum. So, this is what we did in the Lagrange multiplier method. Then we went on to state the Kuhn-Tucker conditions, which are necessary conditions for any optimization problem to be satisfied. So, the more general optimization problems are stated as minimize or maximize f of x subject to g j of x less than or equal to 0 or greater than or equal to 0 and so on. So, you have inequality constraints g j of x less than or equal to 0, g j of x greater than or equal to 0 and so on. And you have a function f of x of n decision variables x 1, x 2, x 3 etcetera x n. For such a general optimization problem, we state the Kuhn-Tucker conditions as follows. This is for the particular combination of minimization of objective function subject to Gj of x less than or equal to 0. So, you have the objective function as minimization and the constraints are all of the form Gj of x less than or equal to 0. Then the Kuhn-Tucker conditions are stated as df by dxi. This is a first order derivative of the original function df by dxi plus j is equal to 1 to m lambda j dgj dxi, where gj of x is the constraint function. So, you take the first derivative with respect to each of the variables and this condition you write for each of the variables. So, you have n number of conditions here and then lambda j gj is equal to 0, gj less than or equal to 0 and lambda j greater than or equal to 0. So, you have n number of conditions associated with this, m number of conditions associated with this, m conditions associated with this and m conditions associated with this. So, you have n plus 3m conditions here. What we do is we take the first n plus m conditions, which are in fact equations, n plus m equations, to solve for the n plus m variables, namely x1, x2, x3 etcetera xn, lambda 1, lambda 2 etcetera lambda m. So, you use these first n plus m equations to solve for the n plus m variables and then examine whether the solutions that you so obtain satisfy in fact these two conditions, lambda gj is less than or equal to 0, which are the original constraints, and lambda j greater than or equal to 0. So, we use the last two conditions to examine whether the solutions that we obtain from the first two conditions in fact satisfy these conditions. So, this is the way we apply the Kuhn-Tucker conditions. I again repeat, Kuhn-Tucker conditions are necessary conditions, they are not sufficiency conditions, except for a specific type of problems where the objective function is convex and you are looking for a minimization and all the constraints are convex functions. So, the objective function is a convex function of the variables and all the constraints are also convex functions of the variables. Such problems are called as convex programming problems. The Kuhn-Tucker conditions that we just stated will also be sufficient conditions only in cases of convex programming problems. I also indicated the variants of the Kuhn-Tucker conditions, where you may have maximization of f x subject to gj of x less than or equal to 0, in which case lambda j will be negative. You may have maximization of f x subject to gj of x greater than or equal to 0, in which case lambda j will still remain greater than or equal to 0. We may have minimization of f of x subject to gj of x greater than or equal to 0, in which case lambda j will be less than or equal to 0, which means in this general form that I have stated, you change one of the conditions, then the lambda j will be changing their sign. That is, instead of minimization, you have maximization, then lambda j will be less than or equal to 0 subject to gj of x less than or equal to 0 and so on. If you change both of them, the lambda j's will still retain the same sign as I have indicated here. The gj of x less than or equal to 0 will correspond to the original constraint. So, if you have gj of x greater than or equal to 0, then that particular constraint will come as a condition here, one of the conditions here. So, when we are applying the KT conditions, the Kuhn-Tucker conditions for a optimization problem, we solve for the stationary point using the first n plus m equations and then examine whether the solutions that we obtain satisfy the other two conditions. You may have several solutions arising out of the first two conditions. We examine the satisfaction of these two conditions for each of these conditions, and then out of several solutions that you have obtained, maybe 1, 2 or some number of solutions satisfy all the conditions, and these correspond to the stationary points of the problem. Let us look at one simple example to drive home the point of use of Kuhn-Tucker conditions. Let us look at maximization of a function f of x is equal to minus x 1 square minus x 2 square plus 4 x 1 plus 4 x 2 minus 8, subject to x 1 plus 2 x 2 less than or equal to 4, 2 x 1 plus x 2 less than or equal to 5. There are two constraints and two variables here. Because we are talking about maximization of the function subject to gj of x less than or equal to 0, the Kuhn-Tucker conditions we write as df by dxi plus j is equal to 1 to n lambda j gj dgj dxi, the partial derivative of the jth constraint with respect to the ith variable. This we write for I is equal to 1 comma 2. So, you get two equations corresponding to this, and then lambda j gj is equal to 0, we write it for j is equal to 1 to 2, gj less than or equal to 0, we write for j is equal to 1 to 2, and lambda j less than or equal to 0. Why less than or equal to 0 here? Because our objective function is maximization and the gj of x are all less than or equal to 0. So, that is why lambda j must be less than or equal to 0. So, we state the Kuhn-Tucker conditions and then start applying the Kuhn-Tucker conditions to examine the stationary points, to determine the stationary points for this optimization problem. So, f of x is given here, then g of x, as I mentioned in the last class, we expressed the constraints as g of x less than or equal to 0. So, you take express g 1 of x as x 1 plus 2 x 2 minus 4 and g 2 of x as 2 x 1 plus x 2 minus 5. Look at the first Kuhn-Tucker condition. We write this for I is equal to 1. So, df by dx 1 plus lambda 1 dg 1 by dxi for I is equal to 1 plus lambda 2 dg 2 by dxi is equal to 0. This we write for I is equal to 1 and I is equal to 2. So, you generate two equations corresponding to this. F of x is this. So, we will write that, and dg of dg 1 by dx 1 is 1 here. I am differentiating this with respect to x 1. Similarly, dg 1 by dx 2 is the differential of the first constraint with respect to the second variable, and that comes to 2. Similarly, you take the second constraint, which is 2 x 1 plus x 2 minus 5, differential of the second constraint with respect to the first variable, second constraint with respect to the second variable. So, these are the values that you obtain. Now, we start applying the Kuhn-Tucker conditions. So, the first condition with respect to I is equal to 1, df by dx 1 plus lambda 1 dg 1 by dx 1 plus lambda 2 dg 2 by dx 2 is equal to 0. So, df by dx 1, my f of x is here. Therefore, df by dx 1 will be minus 2 x 1 plus 4. I am differentiating with respect to x 1. Then lambda 1 dg 1 by dx 1, dg 1 by dx 1 is the differential of the first constraint with respect to the variable x 1, that is 1, and therefore, this will be lambda 1 plus this is 2. Therefore, this will be 2 lambda 2 equal to 0. This is the first condition. Similarly, with respect to the second variable, that is I is equal to 2 now, we will write, and that equation will be minus 2 x 2 plus 4 plus 2 lambda 1 plus lambda 2 is equal to 0. So, you get equations 1 and 2 corresponding to the first set of conditions, namely this condition df by dxi plus lambda plus summation j is equal to 1 to 2 lambda j dgj dxi. This is written for I is equal to 1 to 2. So, you get two equations associated with the first set of conditions, and these are the two equations. Then you also look at the next set of conditions, namely lambda j gj is equal to 0 written for j is equal to 1 and 2. So, lambda 1 into g 1, this is g 1, g 1 of x is x 1 plus 2 x 2 minus 4 is equal to 0. Similarly, lambda 2 into g 2 is equal to 0. So, you have 4 equations now, 1, 2, 3 and 4. You have variables x 1, x 2, lambda 1 and lambda 2. So, you can solve all these 4 equations simultaneously to get x 1, x 2, lambda 1 and lambda 2. Let us say we use equations 1 and 2 now. These 2 equations we use and then express lambda 1 and lambda 2 in terms of x 1 and x 2. These are fairly straightforward solutions, but let us go through it, because you get several combinations and each combination leading to certain sets of solutions, and then we need to examine the other conditions associated with each of these solutions. So, let us start with these 2 equations, equation 1 and 2. From these we express lambda 1 and lambda 2 in terms of x 1 and x 2. So, lambda 2 I take these 2 equations and then express lambda 2, I eliminate lambda 1 from here and express lambda 2 as 4 x 1 minus 2 x 2 minus 4 divided by 3. Similarly, I express lambda 1 using these 2 equations and using the value of lambda 2 that I just obtained as lambda 1 is equal to minus 2 x 1 plus 4 x 2 minus 4 divided by 3. Now, you have equations 3 and 4, which are lambda j g j is equal to 0. We have now expressed lambda 1 and lambda 2 in terms of x 1 and x 2. So, we reformulate these equations 3 and 4 as equations 5 and 6. So, I am expressing lambda 1 here and lambda 2 here in terms of x 1 and x 2, and these are g j of x is equal to 0. Now, for these sets of equations, what we then do is that we take this to be 0 along with this to be 0, this to be 0 along with this to be 0, this to be 0 along with this to be 0, this to be 0 along with this to be 0. Therefore, we formulate 4 different sets of equations to solve to obtain 4 solutions, and associated with each of these solutions we examine the conditions g j x less than or equal to 0 and lambda j less than or equal to 0. So, this is how we proceed. So, for the first terms in both the equations, that is 5 and 6, I take minus 2 x 1 plus 4 x 2 minus 4 is equal to 0, 4 x 1 minus 2 x 2 minus 4 is equal to 0. We obtain the solutions x 1 is equal to 0, I am sorry, x 1 is equal to 2 and x 2 is equal to 2. Using these, we now examine whether the other 2 conditions are satisfied, namely g j of x is less than or equal to 0, which are the original constraints, and lambda j less than or equal to 0, which is the requirement of the KT conditions. So, we substitute x 1 is equal to 2 and x 2 is equal to 2, which is one of the 4 solutions that we need to obtain. For this solution, we examine the conditions g j less than or equal to 0 and lambda j less than or equal to 0. So, you put for lambda 1, you have the expression minus 2 x 1 plus 4 x 2 minus 4 divided by 3, and this turns out to be 0, and lambda 2 is equal to 4 x 1 minus 2 x 2 minus 4 divided by 3, this turns out to be 0. This is expected because these conditions that we have obtained here, these are in fact the lambda values, lambda 1 and lambda 2 values, and you are setting it to 0, and therefore, you get lambda 1 is equal to 0, lambda 2 is equal to 0, and therefore, lambda j less than or equal to 0 is in fact satisfied. We then go to g j of x less than or equal to 0. When you substitute the values of x 1 and x 2, you get g 1 of x is equal to 2 and g 2 of x is equal to 1, which are not both less than or equal to 0. And therefore, this set of conditions is not satisfied by the point 2 comma 2, which you obtained as the first set of solutions. So, this condition is not satisfied, and then we move to other solutions. In fact, even if this set this point satisfies all the conditions, we still exhaust all the solutions to examine how many stationary points we can obtain. So, this condition is not satisfied, therefore, we proceed to the next set of solutions. How do we obtain the next set of solutions? We take the second terms of equations 5 and 6. These are the equations 5 and 6. We initially took these 2 sets, we take now these 2 sets and then obtain the solutions. So, we take these two sets of equations and obtain x 1 is equal to 8 by 5 and x 2 is equal to 6 by 5. With these now, we again examine whether g j of x is less than or equal to 0 and lambda j is less than or equal to 0 are satisfied. Lambda j you get as minus 4 by 5 and lambda 1 you get as minus 4 by 5 and lambda 2 you get it as 0. Therefore, this condition is satisfied. Now, you look at g 1 x and g 2 x. So, g 1 x is 0, it turns out to be 0 with these x 1 and x 2, and g 2 of x turns out to be minus 3 by 5, and therefore, this condition is also satisfied. So, the point 8 by 5, 6 by 5 satisfies all the conditions. All the 4 sets of KT conditions are satisfied by these points, this point 8 by 5, 6 by 5. However, we have still not exhausted all the remaining solutions. So, even if we identify one point to satisfy one point as satisfying all the conditions, we still exhaust all the remaining solutions to capture all the stationary points. So, we move to the next solution, where we take the first term in equation 5 and the second term in equation 6 and obtain the solutions as x 1 is equal to 8 by 5 and x 2 is equal to 9 by 5, and then again check for the conditions g j of x less than or equal to 0 and lambda j less than or equal to 0. When we examine for lambdas, you get lambda 1 is equal to 0 here and lambda 2 is equal to minus 2 by 5 associated with x 1 is equal to 8 by 5 and x 2 is equal to 9 by 5, and therefore, this condition is satisfied. However, when we come to g 1 of x, you get g 1 of x is equal to 6 by 5, which does not satisfy the condition that g j of x must be less than or equal to 0, and therefore, this condition is not satisfied. Then we move on and check for other solutions. What are the other solutions? We take the second term in equation 5 and second term in equation 6. These are the equations 5 and 6. Now, we take this equal to 0 and this equal to 0 and formulate the equations. Here we formulate the equations and obtain x 1 is equal to 2 and x 2 is equal to 1. Again we examine whether this point in fact satisfies the other two conditions. We see that lambda j is less than or equal to 0 is not satisfied, whereas g j of x is less than or equal to 0 is satisfied. So, one of the conditions is violated and therefore, this point does not correspond to a stationary point. So, with that then we have exhausted all the solutions. Among all these 4 sets of possible solutions, we see that only one set of solutions satisfies all the conditions, and that point is x 1 star is 8 by 5 and x 2 star is 6 by 5, and that corresponds to the optimal solution. So, in general then the Kuhn-Tucker conditions we apply to a general problem of maximization or minimization of f of x subject to a set of inequality constraints. In fact, as I mentioned in the previous lecture, the Kuhn-Tucker conditions are necessary conditions for any optimization problem. So, any optimization problem must satisfy the Kuhn-Tucker conditions for the solution to be optimal, and Kuhn-Tucker conditions are necessary conditions and are not in general sufficiency conditions. In water resources problems, however, we hardly ever come across such elegantly formulated optimization problems, where we can straight away apply the Kuhn-Tucker conditions and obtain the stationary points and obtain the optimal points and so on. We however come across large number of large sized problems, where the number of variables is very large, typically of the order of thousands of variables, and the number of constraints that you obtain are also extremely large, because you imagine a large river basin in which you are looking at several alternatives of placement of reservoirs, the size of the reservoirs subject to the hydrological constraints and so on. So, typically you are looking at large number of variables and large number of constraints. and such simple applications of Kuhn-Tucker conditions on a classroom type of exercise will not be viable for large scale water resource systems problems. We use algorithmic ways of solutions for such conditions, such large scale water resource problems. And the most important optimization technique that we use in most commonly used optimization technique in water resource systems is the linear programming. So, starting with today's lecture and subsequent few lectures, I will focus on linear programming problems. Just a bit of history of linear programming. When we are dealing with large scale resource allocation problems, the linear programming is a very elegant and handy tool for optimization of such problems. In fact, the linear programming was conceived and formulated first in its general form by a US Army engineer named Danzig during the World War II. During the World War II, the problem of resource allocation was prominent, especially the military resources. They had to allocate to various places, and the problem of linear programming was formulated by a US Army engineer, Air Force engineer, I am sorry, named Danzig. And in fact, he developed the simplex algorithm subsequently for solution of the linear programming problems. Linear programming is so commonly adopted in all branches of engineering that it is said that about 25% of all the problems that are solved on computer are in fact LP problems, linear programming problems. Let us see why and how the linear programming is applied to several problems. We have seen a general statement of the optimization problem, where we have the objective function f of x, which is to be minimized or maximized, which is a function of n decision variables x 1, x 2, etcetera, x n, subject to g j of x less than or equal to 0. You have m conditions. If the objective function f of x is a linear function of the decision variables, if all the constraints g j of x are also linear functions of the decision variables, then such a problem is called as a linear programming problem. In fact, in the general form of the linear programming problem, we also add the condition that all the decision variables x 1, x 2, etcetera, x n are all non-negative. That means, x I is greater than or equal to 0. So, in general you have three conditions to be satisfied, namely that the objective function f of x is a linear function of the decision variables x 1, x 2, etcetera, x n. All the constraints g j of x are all linear functions of the decision variables x 1, x 2, etcetera, x n. Additionally, all the decision variables are all non-negative, x j greater than or equal to 0 for all j. Now, these three conditions lead to the general form of linear programming problem. We will just see some of the features of the linear programming. As I just mentioned, it is a optimization method for solution of problems with objective function and constraints as linear functions of the decision variables. So, both the objective function as well as the set of constraints are all linear functions. Now, this was formulated by Danzig. As I said, he formulated the general LP problem during the World War II and also devised the simplex method of solution. In fact, in the field of operations research, optimization, etcetera, the linear programming is considered as a revolutionary development that permits us to make optimal decisions in complex situations. And as you will see during the application in the applications lectures, where we deal with large scale water resource systems problems, LP becomes a very handy and elegant tool for screening of alternatives, for obtaining optimal reservoir operating policies, for obtaining optimal hydropower generation, obtaining optimal flood control and so on. So, when we are dealing with large scale optimization problems, linear programming problem, mainly because of the simplex, revised simplex and the Kuhn-Tucker algorithm becomes an extremely handy tool for systems analysis. The simplex method, as I mentioned and as we will introduce in the subsequent courses, is the most elegant and efficient and therefore, a very popular method of optimization. The Kuhn-Tucker algorithm, which is developed by Kuhn-Tucker, an Indian, is 50 times faster than the revised simplex method. The general principle of the Kuhn-Tucker algorithm I will explain when I am talking about the revised simplex method. And in the field of water resource systems, a large number of applications exist today of the linear programming problem. In fact, any first cut systems analysis that we do in water resources almost always uses the linear programming. So, there are a large number of applications. For example, you are talking about reservoir operation, multiple reservoir systems operation. Look at systems of Narmada river basin where you have 14 or 15 major reservoirs which have to be operated in an integrated way. So, you are looking at optimization of reservoir operation of large systems. Even when you are talking about a single reservoir optimization, you have multiple functions: water supply, irrigation, flood control, hydropower, downstream water control and so on. So, you have a single reservoir catering to multiple functions, and then you are talking about time periods of the order of 10 days, 15 days within a year. So, you may have 36 time periods within a year, 12 time periods within a year and so on. So, you have sequential optimizations, monthly decisions to be taken over 12 months of a year, and therefore, you may have associated with each set of constraints, you may have 12 number of constraints, and like this you may have several constraints corresponding to mass balance, corresponding to the constraints due to the physical features of the system and so on and so forth. So, you will have large number of constraints associated with even a single reservoir operation problem. So, the size of the problem will be quite large. Then you may talk about irrigation scheduling, where you are looking at allocation of a given amount of water among different time periods, among different crops and so on. So, the irrigation scheduling problem is how much amount of water to be applied during a given time period among several different competing crops. That is the irrigation scheduling problem. We apply linear programming for such problems. Then you may have the reservoir capacity determination. You would like to meet the demands from a river. There is a supply. So, the supply will determine the constraints of water availability, and then you would like to have a given reservoir of minimum capacity to meet a set of demands. So, that is a reservoir capacity determination. I will talk about this problem specifically when we go to the applications. Then you have screening of alternatives in river basin development. Let us say you have a large river basin in which you would like to build several reservoirs, and you would like to use the groundwater at several locations. So, you are looking at where to build the reservoirs, how much capacity of the reservoirs to be built, how much of groundwater to be used in conjunction with the surface water and so on. So, there are virtually infinite number of alternatives that are possible. So, you would like to screen the alternatives. So, linear programming is a powerful technique as a screening technique. So, out of several such alternatives that are possible, all of which will meet the requirements, functional requirements, which among these large number of alternatives are best alternatives. So, these are called as the screening problems. So, for screening problems in water resources, we often use linear programming. Then we also talk about conjunctive use of surface and groundwater, how much of surface water to be used, how much of groundwater to be used, such that the system becomes sustainable over a period of time. Now, these will involve optimal decisions. Let us say 30% of the groundwater, 70% of the surface water during certain time periods. Then you start reducing the use of surface water and then start using the groundwater more, so that you are able to meet the conditions. What are the conditions? As I mentioned in the very first lecture, that you do not want the groundwater to come into the root zone by thus causing the waterlogging, and you do not want the groundwater to deplete so much that it becomes unsustainable. So, you would like to maintain the groundwater level within certain conditions, yet at the same time you are able to meet the requirements, both irrigation requirements as well as municipal and industrial requirements. So, such problems are the conjunctive use problems, and typically in conjunctive use problems, because you have a groundwater model, you have a surface water model, and then the two will be integrated together in an optimization framework. The size of the optimization problem will be really large. Even for very small catchments, small basins, etc., we deal with 30,000, 40,000 constraints, 30,000, 40,000 variables and so on. So, any water resource systems problems, when we want to address the problems in a meaningful manner, the size becomes a major issue, and whenever we are talking about large sized optimization problems, linear programming is provides us with a very handy tool for solution of such problems. Then the resource allocation problems, as I mentioned, it is not just the water resource. When you are talking about developing a river basin, you may be talking about economic resource allocation, the labor resource allocation, the land resource allocation, the water resource allocation and so on. So, when you are talking about allocation of various resources, the linear programming is it is a very elegant and useful tool of optimization. So, as I mentioned, not only in water resources engineering, in most of the engineering optimization problems, linear programming is by far the most widely applied optimization technique for the advantages that it has. However, the requirement that the objective function be linear, all the constraints be linear functions of the decision variables, and all the variables themselves be non-negative, often is not directly satisfied by most of the engineering problems, engineering optimization problems, in which case we adopt some linearization techniques both on the objective function as well as on the constraints to convert the nonlinear objective function and nonlinear constraints into linear objective function and linear constraints. We will look at these techniques of linearization subsequently. Okay, now, what we will do is, we will start with a very simple linear programming problem and look at how we solve the look at the basis for the solution of all the linear programming problems. As I mentioned, you have in the linear programming, you have f x as a linear function of x. X is a vector of decision variables x 1, x 2, etc., x n. You have n number of decision variables. So, the objective function is a linear function of the decision variables. All the constraints are all linear functions of x. So, you may write, for example, 2 x 1 plus 3 x 2 less than or equal to 5, which is a function which is a linear function of the decision variables x 1 and x 2. Whereas, if you have 3 x 1 into x 2 plus 5 x 1 square or 5 x 2 square, etc., this is not a linear function. So, you must have all the constraints also as linear functions. Then, in the general form, the requirement is that all the variables be non-negative. In most of the water resources problems, and in fact, in most of the engineering decision making problems, the decision variables that we will be dealing with are all almost always physical variables. For example, we may be talking about maximization or minimization of the reservoir capacity, maximization of the flood control storage, maximization of hydropower development and so on. So, the variables associated with these will be storage variable, inflow variable, the discharge variable and so on. So, these are in general non-negative. We will be talking about mostly the physical variables, which are all in general positive variables or non-negative variables. However, there may be situations where we may be talking about, let us say, temperature, which can also take negative values. So, there may be cases where you may have to deal with variables which are unrestricted in sign. We will see presently how we deal with unrestricted in sign. And also, as I mentioned, you may have certain situations where your equations are not linear functions, they may be non-linear functions of the decision variables, in which case we adopt what are called as piecewise linearization techniques or linearization techniques to convert the non-linear functions into linear functions for use in linear programming. Similarly, your objective function can be non-linear, we convert that into a linear function. So, the requirement of the general form of LP is that the objective function should be a linear function, constraints should all be linear functions of the decision variables, and all the decision variables be non-negative. When you satisfy, when your optimization problem satisfies all these three conditions, then we use the linear programming problem. Okay, let us look at the simplest form of solution, which in fact provides us with the motivation for the algorithmic way of solutions. Let us say we start with a simple problem. Let us say we are looking at a function of just two variables 3x1 plus 5x2 or some such thing. This is our objective function f of x, and we may be interested in maximizing this. So, we will write maximize f of x is equal to 3x1 plus 5x2. This is a linear function of x1 and x2. x1 and x2 are the decision variables. Then we may write a constraint subject to, let us say x1 is less than or equal to 4 and 2x2 is less than or equal to 12. Let us say we write only these two conditions. Just have a look at this function. We have positive coefficients here 3x1 and 5x2, and we are looking at maximization of this function. So, as I increase the value of x1, my function value increases. So, I would like to have as high a value for x1 as possible. Similarly, because of this positive sign here, as I increase the value of x2, this term increases and therefore, the function value increases. So, I would like to have in this problem as high a value of x2 as possible. To what extent I can increase the value of x1? That is governed by this constraint, x1 should be less than or equal to 4. Typically, this may be a resource allocation problem where my resources are limited and therefore, I cannot increase x1 beyond 4. So, I would like to increase x1 to the greatest extent possible, and therefore, I will make x1 is equal to 4 and therefore, this term becomes 3 into 12. Then 2x2 will be 12, which means x2 is less than or equal to 6. Therefore, I will increase x2 up to 6, so that I get the maximum value of f of x. This is the motivation. That means, we will look at what are the limits up to which we can increase the variables. Now, these are by far the simplest conditions that I put. Let us say that we put another condition that we may have 3x1 plus 6x2 may be less than or equal to I will put some 10 or some such thing. So, I may have another condition which is a function of x 1 and x 2. So, I am putting another condition here, which will we act along with the other two conditions and then decide on what are the optimal values of x 1 and x 2. I am still looking at the maximum values of x 1 and maximum values of 3 x 1 plus 5 x 2, and I keep on adding constraints like this, the problem becomes more and more complex. If I had only this condition, then x 2 would have been infinity. Then I add this condition, then x 1 will go to 4, x 2 will go to 6, and I obtain the optimal value. Then I add one more condition, then x 1 need not go to 4 or x 2 need not go to full 12, because it will be governed by this condition. Like this, as I keep on adding conditions, the values that the x 1 and x 2 can assume become more and more restrictive. So, these sets of conditions in fact will determine whether a given value of x 1 and x 2 is in fact feasible or not. What do I mean by that? Let us say I have a solution x 1 is equal to 5, that does not satisfy this condition, and therefore, x 1 is equal to 5 is not a feasible solution. So, we identify the particular region in terms of x 1 and x 2 in this particular case, in which all the conditions are satisfied, and that will determine what is called as a feasible solution or feasible range, feasible space. We will understand this better when we use only two variables and a set of constraints and use the graphical procedure to see what is happening. Let us look at such a simple problem now. So, I will now demonstrate the use of the graphical procedure for solution of linear programming problem, and because we are using graphical solution, I will use only two variables, so that the principle is understood correctly, and then we will lead this from the graphical solution, we will lead to more complex algorithmic approach, not more complex, more rigorous in fact, algorithmic approach of simplex method. Let us look at two variable problem with a set of constraints. So, in the graphical method, we are looking at a physical picture of the geometric characteristics of the LP problem, and this is best used only with two variables. In fact, in the classroom type of examples, we can use only with two variables. As the number of variables increases, the graphical picture becomes more and more complex, and therefore, it is unwieldy, it becomes unwieldy. But however, to understand the basis of the solutions for linear programming, we will use the graphical method. Let us look at a simple problem. We are looking at maximize z is equal to 3 x 1 plus 5 x 2. In fact, in LP problems we use, instead of f of x, we use z as the objective function, notation for objective function. So, you have such a simple function 3 x 1 plus 5 x 2 subject to x 1 is less than or equal to 4, 2 x 2 less than or equal to 12, 3 x 1 plus 2 x 2 less than or equal to 18, x 1 is greater than or equal to 0 and x 2 is greater than or equal to 0. Now, these are the non-negativity conditions. Look at the objective function. It is a linear function of the decision variables x 1 and x 2. So, the objective function is a linear function. These are the sets of constraints. X 1 is less than or equal to 4 is a linear function of x 1. 2 x 2 is less than or equal to 12 is a linear function of x 2. 3 x 1 plus 2 x 2 less than or equal to 18 is a linear function of x 1 and x 2. So, all the constraints are linear functions of the decision variables x 1 and x 2, and additionally you have the decision variables as non-negative. So, the non-negativity conditions are stated as x 1 greater than or equal to 0, x 2 greater than or equal to 0. Now, to solve this by a graphical method, what we notice is that because of the non-negativity conditions x1 greater than or equal to 0, x2 greater than or equal to 0, in the 4 quadrants that we have in the 2-dimensional space, the solution must lie in the first quadrant, because x1 greater than or equal to 0, x2 greater than or equal to 0. So, what we do is that we first draw the axis. This is the x1 axis, this is the x2 axis, and because x1 is greater than or equal to 0, I am looking at this region x1 greater than or equal to 0, and because x2 is greater than or equal to 0, I am looking to the right of this axis. Therefore, the solution lies in the first quadrant. Then I look at the and therefore, I mark the first quadrant. So, the solution has to lie on the first quadrant here, because of x1 greater than or equal to 0, x2 greater than or equal to 0. Then I look at the conditions. We have the condition x1 less than or equal to 4. To mark this condition, what I do is I take x1 is equal to 4, because I want to increase x1, and I am putting a bound of x1 is equal to 4. x1 cannot be greater than 4. So, x1 cannot exceed beyond 4. So, I draw a line x1 is equal to 4, which in fact determines the bound on x1, and because I want x1 less than or equal to 4, I look towards the left of this. So, any region within this will satisfy this condition, namely x1 is less than or equal to 4. Then I look at the second condition, which is 2x2 is less than or equal to 12, or x2 is equal to 6. So, this line is x2 is equal to 6, and I have to look below this, because x2 cannot be more than 6. So, I am looking below this. Just look at what happened. The moment I considered these two conditions, I have defined a region here. In this region, both these conditions are satisfied. Any point outside of this region, at least one of the conditions is violated. Therefore, that becomes an infeasible point. So, by drawing these two conditions, these two constraints, I have identified a region in which these two conditions along with the non-negativity conditions are satisfied. Now, we look at the third condition. Third condition is 3x1 plus 2x2 is less than or equal to 18. Now, 3x1 plus 2x2 less than or equal to 18 is this line. How do I draw the line? I put x1 is equal to 0, I get x2 is equal to 9. So, 0, 9 is 1 point. I put x2 is equal to 0, I get x1 is equal to 18. Therefore, 6, 0 is another point. So, I join these 2 points. By joining these 2 points, I draw the line 3x1 plus 2x2 is equal to 18. What did I do? And because I want this to be less than or equal to 18, I am looking at this direction now. So, because of this condition now, I have now found another region where all the 3 conditions are satisfied. So, I mark this region now. This is the region in which all the conditions are satisfied, all the 3 conditions are satisfied. And this in fact becomes the feasible region of the problem. Remember, I have not looked at the objective function yet. I am only looking at the set of constraints. These are the non-negativity conditions, x1 is greater than 0, x2 greater than 0, which makes my solution possible only in the first quadrant. Then I looked at x1 less than or equal to 4 by drawing a line x1 is equal to 4, and then say that my solution should lie to the left of this line. Then I drew 2x2 less than or equal to 12 by I drew 2x2 is equal to 12, which defines the bound on this condition. I have to look to the down to the below of this condition. Then I draw the line 3x1 plus 2x2 less than or equal to 18, and then form this constraint. The intersecting region of all these constraints along with the non conditions is this region. This region is called as the feasible region. in this feasible region, you take any point within the feasible region, it satisfies all the conditions, and that is why it is called as a feasible region. So, any point lying within or on the border of this region satisfies all the conditions. How many such points are there? There are infinitely many points, infinite number of points which will satisfy all these conditions. Among these infinite number of points, we want that particular point which maximizes this condition. So, we have still not looked at the objective function, we have simply identified the feasible region. The feasible region consists of infinitely many points, and among these infinitely many points, we want to choose or we want to identify, determine that particular point which maximizes the objective function 3x1 plus 5x2. How we do this? We will continue in the next lecture. So, in today's lecture, essentially we started with an example of use of the Kuhn-Tucker conditions, and Kuhn-Tucker conditions are the necessary conditions that any optimization problem has to satisfy. So, essentially what we do is we use the first two sets of conditions to determine the n plus m variables, which in fact determine the stationary point, and then we examine corresponding to these stationary points, we examine whether the other two conditions are satisfied. In the example problem, we examined whether g j of x less than or equal to 0 and lambda j less than or equal to 0 are satisfied. We do this for all possible solutions that we obtain by solving the first two sets of conditions. So, in the example we had 4 sets of solutions, we do the examination for all the 4 sets of solutions, and out of the 4 sets in the example problem we saw that only one of them satisfies all the conditions. In different types of problems you may have more number of solutions satisfying all the conditions. All of these will form the stationary points. Kuhn-Tucker conditions are not sufficiency conditions in general, except for the problems of except for the problems that are known as convex programming problems, in which the objective function as well as the constraints, all of which are convex functions of the decision variables x1, x2, etc., xn. Then we went on to introduce the linear programming problem. In the linear programming problem, the objective function has to be a linear function of the decision variables. All the constraints are all linear functions of the decision variables, and additionally in the general form of the linear programming that we will be using, the decision variables are all non-negative. So, we typically write x j is greater than or equal to 0. So, when we satisfy, when an optimization problem satisfies all these 3 conditions, then we say it is a linear programming problem. Then we have just introduced the graphical method of solution, where we first draw the constraints, the bounds determined by the constraints, and identify the feasible region. So, the feasible region is that region in the solution space where any point within the region or on the boundary of the region satisfies all the constraints. So, the first step in the linear programming solution by graphical method is to identify the feasible region. So, there are infinitely many such points which satisfy, which all of which satisfy the constraint, set of constraints. Among these infinitely many points, we have to identify one particular solution, which is in fact the optimal solution. We will see how to do this in the next class. Thank you for your attention.